Okay, well, I guess we'll get started then. And so I have decided to cancel tomorrow's quiz. Okay. Okay. I'm glad you guys are happy. So no quiz tomorrow. We'll just cover. We're gonna get into hypothesis, and I'm also skipping section 7.5 in the text. So we're gonna just no. All right, enough. What?
What about the final?
You're gonna have a final, definitely. Okay. I would get in trouble. But anyway, no, I don't want to be the one adding to your life's miseries. So. Anyway, so no quiz tomorrow. I've told the TAs to cover hypothesis testing during that time. We'll cover hypothesis testing today. We'll cover hypothesis testing on Friday. We're gonna see hypothesis testing for a little bit of time here. Okay. We will have a quiz next week in week 9, and then no quiz week 10. So anyway. Yeah, it's just 3 weeks of instruction, and then your final exam, and then you'll have spring break, right? So you'll miss me. I'll miss you guys too. So yeah. I do sincerely hope that the class has been of educational value to you, and that you have enjoyed the class. What? Yeah. Give me. Okay, that's great. Yes. So if if you liked the class, I would appreciate you giving me your highest reviews. So this is my first year as a lecturer. I don't know if you guys know that. This is my first year as a full-time lecturer. So your reviews are very important. In terms of me getting rehired for the next year. so anyway, it does play a big part for lecturers' careers in the first few years. Also, if you like the class, I would appreciate a review also on Bruin Walk. Okay, so but anyway, you can wait till the class is over. You don't have to write anything here. And I promise I'm not trying to bribe you or anything by canceling the quiz tomorrow. I decided, because I just realized, we had a midterm on Friday, and I'm like, all I'm done is teach on Monday and today, so it seems kind of short to have a quiz. So anyway, we'll get into hypothesis testing. This is it's an exciting topic, I promise you guys. Okay, so just FYI, we will skip section 7.5 in the text. Okay, if you're interested, you can go back and read 7.5. Basically, if you understand section 7.4 and what they're talking about with confidence intervals, 7.5 is just a little bit of an extension of that, okay? But I do feel like the more important topic would be hypothesis testing, and I want to spend some time focusing on this, okay? So hypothesis testing, this is a tool for us to make conclusions about the population based on a sample, okay? Or later on, or samples, okay? So again, I feel like I've drawn this picture many times. We've got the population too big to observe, so we just take a little piece out. This is our sample, okay? And we look at the sample, and based on what we see in the sample, we make conclusions about the population. So this is statistical inference. Okay, making conclusions with limited data. Okay, so let me kind of just tell you not a story, but give an illustration of kind of the big picture of hypothesis testing. Okay, the question, the big question is, what is the probability of observing our data? Okay. What is the probability of observing our data, you know, if some, quote, scenario were true? All right, so I'm going to kind of illustrate this, and then we'll formalize this concept of the probability of observing our data if some scenario were true. Okay? So if you go to an amusement park, other than Disneyland, Disneyland is too classy for this kind of stuff. If you go to an amusement park, other than Disneyland, a lot of times there's kind of this section where there's carnival games, right? Or I guess if you go to a carnival or state fair, they have carnival games, okay? And you know, they're all kind of like, you know, do something stupid, and you know, pay money to try, and maybe you win a teddy bear, okay? Now, if you have a shady carnival stand, they might have actually rigged the game so that you are at a disadvantage, okay? And you know, what the game appears to be may not actually be how it is, okay? So let's say there's some carnival game. I'm sorry? Oh, I'm off the screen. So, okay. Some carnival game, all right? And we'll just keep it a simple game. Let's say it's like spin the wheel, all right? Spin a wheel. And this, you know, the wheel is set up where, okay. So, you know, what it appears is that you have a 0.5 chance of winning. Okay? All right, so you know, you spin the wheel, you're supposed to win half the time. Maybe half of the spaces are painted to be winners. Okay, let's say you play the game 10 times. So this will be case 1. Okay, let's say you play 10 times. You play the game. Okay, if you play the game 10 times, how many times do you expect to win? It's not a trick question. Yes, we would expect to win 5 times, right? Let's say you play the game 10 times, okay? We would expect to win 5 times, okay? And let's say what actually happened, okay? What actually happened? You won 3 times. Okay. So you won fewer times than what you expected, okay? Are we now going to then accuse the carnival game operator and say, hey, you've set this game up so that you've rigged the game so I'm gonna lose? Would we say that? No, right? Like, so if the question was, does this being the fact that I only won 3 times, okay? That I only won, I'll say only won 30% of the games. When I expect to win 50% of the games. Okay, so does this provide evidence that the game has been rigged against us? Okay. Craning their neck. So, okay. What's your gut reaction? No, right? Our reaction is not really. Does this provide evidence? We would say no. What we feel like is you just happen to be a little bit unlucky, right? You were, I'm just gonna write, we could have just been unlucky. Unlucky and won only 3 times. Okay, that's what happens when you play games of chance. Sometimes you get unlucky. All right, and winning 3 games out of 10 when the probability is 50% to win, this doesn't seem that unreasonable, okay? On the other hand, does this prove that the game is not rigged? No, okay? Right now, it's just, you've played 10 games, we can't really say it's rigged or it's not rigged. It's just, maybe we just got unlucky, okay? So this, but, keep in mind, has been rigged. I'm sorry. But keep in mind, this does not prove that the game, is 100% fair either, okay? So it proves, it neither proves that it's fair, but it also doesn't provide evidence that it's unfair. Okay, so that's case 1. All right, this case 2, exact same thing, okay? I'm going to just copy this over. Next slide. Okay, case scenario 2. This time we're going to play 100 games, or 200 games. Okay, so scenario 2. Okay, now we play 200 games. Okay, so we expect to win 50% of the time, which translates to 100 wins. Okay. What happens? We win 60 times. Okay, which translates to 30% win rate. Okay. Okay, so now the question is, do our results here cause us to suspect that the game is rigged? Yeah, so here, so the question, it's actually the exact same question that I had over here. Does this, so I'm just, sorry, I have the magic of cut and paste. You don't. So this is the exact same question we're going to ask. Does this, the fact that I only won 30% of the games when I expect to win 50% of the games, provide evidence that the game has been rigged against us? Okay. And so what's your gut instinct here now? What's that? Maybe, maybe not, yes? Okay, so I feel like, you know, if you played 200 games and you only win 30% of the games, I feel like you'd start to suspect that something is messed up here, okay? So here we would say, you know, yes, at least our gut tells us so, okay? Gut says so, okay? And the thing is the question is, is it technically possible that I could have just been really unlucky? Technically, it's possible that I could have been really unlucky. However, we feel like we would have to be super unlucky to have won only 30% of the games, okay? So I guess technically, it is possible that I was unlucky and won only 30% of the time. Okay, but it feels like we would have to be super unlucky. For this to happen. Okay, and so indeed, you know, the question is, what's the probability that a fair game would produce only a 30% win rate after 200 games? Okay, so what's the probability of us getting the data that's a 30% win rate after 200 games under the condition that it's actually playing fair, 50%? And we can do the math, and that probability is incredibly tiny, okay? So I'm gonna write this down. Let me see. What is the probability of winning only 30% of 200 games if the game is fair, meaning 50% win rate? Okay, so what is the probability of that happening? Okay, that probability is incredibly tiny, okay? This probability is very, very small. Okay, and so what this means is that, yeah, technically it's possible that I was unlucky, okay? But I would have to be super unlucky, like almost like winning the lottery of unluckiness, and I just don't think that would have happened. And so it's easier for me to just conclude, I think the machine is rigged or the game is rigged against me, rather than saying, oh yeah, I just happened to win the unlucky lottery, okay? I mean, you could have won the unlucky lottery, but most likely, you know, something like this happens, you're gonna say, I'm gonna just kind of ignore the possibility of winning the unlucky lottery and just conclude that the game is rigged, okay? That's kind of like, that's the easier explanation, okay? So the probability is very small, so we will conclude that the game is rigged. Okay. So this is the big picture of hypothesis testing. Okay. Basically, you're just asking the same question. Okay. And depending on your data, you're just asking, what's the probability of us getting this data if we assume this to be the case? So we're basically saying, okay, for argument's sake, let's say the game is playing fair. What's the probability I win only 30% of the games if I play 200? Okay, and that turns out to be incredibly small. On the other hand, if we say, okay, for argument's sake, let's say the game is playing fair, what's the probability that I win only 3 games out of 10? Okay. Well, it turns out that winning only 3 games out of 10 is a rather common occurrence. Okay, and because it's a rather common occurrence, we can't say, we can't ignore this possibility that I just happen to be unlucky. So that's the difference. Were we unlucky? Could it have just been bad luck that we won so little? Or is it, I mean, that's always a possibility. But you kind of draw a line and you say, I don't think it was just bad luck. I think something else is going on here. Okay? So we're going to break hypothesis testing out into kind of 4 steps, and we'll go into detail for each of these 4 steps, and we'll work through this. Okay, so kind of hypothesis testing. In 4 steps. Okay, so number 1. Create your hypotheses. Okay, and so the hypotheses always come in pairs. We have a null hypothesis and an alternative hypothesis. And you know what? I'm going to just list off all 4 steps here, and then we'll go into each of these in detail. Okay. 2 will be preparation. So the preparation will be picking a significance level which we call alpha. And then labeling our data. 3, this will be our calculations. Okay, so ultimately we want to find something called the p-value. Find our p-value. And this generally involves calculating a standard error. So this involves finding the standard error and test statistic. And then lastly, interpret and make conclusions. Okay, and so what we do is we compare our p-value to alpha. Okay. Today's going to be more just of this me talking day. I don't know. Okay, so here we go. Hypotheses. All right, so let's talk about hypotheses. Okay, so we have the null hypothesis, okay? And the null hypothesis, this is kind of like the quote status quo. The status quo, or this is, in general, we hope to disprove the null hypothesis, but not always, okay? Hope to show that the null hypothesis is wrong. Okay, so we call this HO, not HO, and this is HA, the alternative hypothesis. This is the other possibility. Okay. So, in the case of our carnival game example, okay, the question was, do we have evidence that the game, is rigged against us? Okay, so in this case, we've got kind of a null hypothesis and an alternative hypothesis. And what we're going to have is the null hypothesis will state that the game plays fairly. Okay. And what the alternative will state is that the game the game is rigged against us. Okay. And the truth is either the null or the alternative is true. Okay. So if the null is true, then our data is purely the results of random chance. Okay, so maybe, if the null is true, then that means if we're winning only 30% of the time, we're winning only 30% of the time because we're unlucky. That's it. Okay? If the alternative is true, okay, then our data results from chance plus the fact that the game is rigged. Okay. So these are our hypotheses stated in words. In general, we don't really write out all of the words in hypothesis testing, and we just kind of shortcut this, and we use symbols, okay? So symbolically, we would say something like P is the actual true win rate of the game. And the null hypothesis would be that P is equal to 0.5, meaning that the game actually plays fair and that the true win rate of the game really is 0.5. The alternative hypothesis would be, hey, the game is rigged against us so that the true win rate of the game is not 0.5, but is less than 0.5. Okay. Okay. So just kind of a note. I'm gonna write this, and I'll say, do not say that the null hypothesis equals 0.5. Okay. So notice that the null hypothesis, then there's a colon, is a statement. Okay. So the null hypothesis is a statement that says p is equal to 0.5. The null hypothesis itself is not 0.5. Okay. The null hypothesis is a statement about p. Okay. And then the hypotheses are always about population parameters. So the hypotheses are always about population parameters. So you would never use p hat in a hypothesis, okay? Because p hat is a sample proportion. So p hat would never show up in a hypothesis. Later on, we'll learn hypothesis testing for means and stuff like that. And so in that case, the hypotheses will always use mu and never x bar, because x bar is for a sample, mu is for the population. Okay, let me just say just a few other key points. Okay, so a few tips for writing hypotheses. Okay, the null hypothesis will always have an equal sign. Equal sign in it. Okay, and then the alternative will have either greater than, less than, or not equal to. The okay. If there, whatever value appears in the null hypothesis, the same value appears in the alternative. So if you've got, so our example was the null hypothesis stated something like p is equal to 0.5. So our alternative was p is less than 0.5. Okay. Whether you choose greater than, less than, or not equal in the alternative depends on the question. So if the question says something like, so generally the questions will be like, does the data provide evidence that ... Okay, so if it says something like the proportion is more, proportion is things like greater, larger, more, higher, etc. Okay, use greater than. Okay, less, smaller, fewer, lower, whatever. Okay, that's going to point to less than. Okay, and then if you see things like is different, changed, not the same, whatever, then you're going to use a not equal sign. Okay, so this is all just to establish your hypotheses. Okay, and then what do we have? What do we have? Okay, so then part 2 is our preparation. Okay, the significance level, or alpha, is the line where we decide if a probability, if the probability of our data is large or small. Okay, so remember, if you just think back to our carnival game example, we said, you know, the probability of winning 3 games out of 10 just from bad luck, that there's a decent chance that would happen. So in that case, we said the probability is large, so we're not going to conclude that the game is rigged. On the other hand, the probability of winning only 60 games out of 200 from, quote, bad luck, that's incredibly unlikely to happen. So in that case, we say the probability is super small, so we're going to conclude that the game is rigged. Okay? And so we have to choose where we're going to draw this line. Okay? So where should we draw alpha as the line between what's big and small? This is kind of your choice. Just for whatever reason, over time, alpha equal to 5% has become the normal value, the regular choice. Okay, so if a problem doesn't tell you what alpha to use, just assume that it's 0.05. Okay, so if no alpha given, assume alpha is 0.05, okay? But depending on the circumstance, you may want to use a larger or smaller alpha. So, 5%, it's an arbitrary line. It's kind of become the gold standard, though, and there has been some criticism of it because, the true value should be somewhere around 5%, but there's nothing magical about 5% in of itself, okay? But, there's a lot of things in life where, we just draw arbitrary lines and then we accept it as fact. If you think about it, why are 16-year-olds allowed to drive? Like, is there something magical that happens on someone's 16th birthday that suddenly gives them the capability to handle a, multiple, 5,000-pound object traveling at 60 miles per hour? No, nothing magical happens on someone's 16th birthday, but we've accepted that this is the point at which someone can handle such a responsibility. Who knows, okay? So we got that, okay, and then labeling your data, okay? So label your data. So in our case, we are doing hypothesis tests. So I'm going to just abbreviate this. HT for proportions based on one sample. Okay, so we need to label our n, an x maybe, if and a p hat. Okay, so the x is a maybe. Okay, sometimes. Okay, so you got to figure out your n, your x, your p hat. Okay, maybe you don't get x. P hat is generally x over n, but perhaps x is not given to you and they just give you p hat directly. All right, I'm trying to think here. So we're not gonna cover enough for me to really ask you guys questions. So maybe I'll just, today, I'm just gonna use the clicker to take attendance, I guess. So we'll just give you guys all points for free to take attendance. So let me just do this. You guys just want me to ask like a couple questions for free points? Sure. Okay. All right. Okay. So first question, we will say the answer is A. So everybody just click A. All right. Go. All right. All right, Divert. Okay. Everybody got their clicks in? All right, great. What's that? So who clicked B and C? All right. Okay, I can't. Whatever's all right. Yes. Oh, hypothesis test. Yeah. Hypothesis test for proportions based on one sample. Okay. All right, so then part 3 would be our calculations. Should I ask just like a dumb trivia question? I don't know. What's a silly, how old am I? No, I don't want to tell you. Okay, sure, we'll go there. All right. How old am I? All right, what do you think? I have no idea. Oh, I'm scared what you guys are going to say. All right, let's just hear some, shout out some numbers here. Okay. We'll, all right, we'll say 28, 29, 30. No, this is too hard? Okay. That's like impossible? All right. 28, 30, 32, 34, 25. All right, let's just see. I'm just curious what you guys think. This is the hardest question I've asked. All right. Okay, so get your clicks in. All right, let me talk about the calculations we got to do. All right. So all of this is based off the idea that we're going to go for something called a p-value, okay? And the p-value is the probability of observing our data if the null hypothesis were true. Okay. So, in our null hypothesis, we have p equal to some number here, okay? Now, unfortunately, this number we call p0. But in our carnival example, I think makes more sense to say our null hypothesis is p is equal to 0.5. All right? And so the way this works is we say, well, if the null hypothesis were true, then whenever we play a bunch of games, I would expect to win about 50% of the games. Okay. Now, because of random chance, I might win more than 50%. I might win less than 50%. I'm going to stop the timer here. Okay. So because of random chance, I might win more than 50% or I might win less than 50%. What happened in our data? We only won 30%. So what's the probability that I only get 30% or less? Okay, so actually, what's the probability of observing our data, and then it's or something more unusual? Sorry. Or something more unusual. Okay, so the probability of observing our data if the null hypothesis were true or something more unusual. Okay, and so the way we're going to do this is just like what we did in chapter 7. We calculate our standard error. Our standard error is based on our distribution here, so what we use is p0 times 1 minus p0 over n. So p0 is the value that shows up in your null hypothesis. Okay, and then we get a z-score. So z is going to be the difference between what we observed in our data, p hat, minus the value that we expect under our null hypothesis, in this case 0.5 or p0, divided by our standard error. Okay, so we get our z-score, and then we look up z in the table to get our p-value, our area. Okay. We're going to run out of time here, but okay. So I'm going to just we'll pause here. I'll tell you my answer here. I am 32. Oh, okay. All right. Yes, I'm 32. I'm married with children, so or with it, we'll just want one child. So here we are. Okay, we'll end here and we'll continue on here. We'll see you guys on Friday. No quiz tomorrow, so enjoy your day.